In the following material, we will present two case studies from Romania: a water treatment plant and a municipal wastewater treatment plant. The first case study refers to a water treatment plant for Iași municipality. The water sources used for water treatment for drinking purposes consist of a surface water source, the Prut River, and the groundwater source, Timișești. The natural sources for supplying water to populated areas and industries are distinguished from each other by their qualitative characteristic, flow regime, and option for collection and treatment. In this slide, we can observe some representative images from the drinking water treatment plant in Iași. Some important information related to drinking water treatment is presented by Apa Vital, which has prepared a short video explaining how drinking water can be obtained. The second case study refers to a municipal wastewater treatment plant. Wastewater treatment plants contribute to the removal of pollutants generated by municipalities and industry and to the minimization of their negative effect on environmental quality and human health. However, they are also come with a series of disadvantages such as high operational and maintenance cost, the generation of sludge and greenhouse gases, and the requirement of large land areas. This slide presents the technological scheme of a typical municipal wastewater treatment plant, which include the following stage. Pre-treatment stage, where physical processes are employed to remove solid substances of various sizes. Primary treatment, which allows for the initial reduction of organic and suspended substances. Secondary treatment used to eliminate biodegradable organic matter through biological process. And tertiary treatment refers to processes either before or after biological treatment that further improve the efficiency of the treatment plant and the quality of the effluent. The sustainability of municipal wastewater treatment plant was evaluated by using a CAM tool. The municipal wastewater treatment plant considered for this study serve a resident population of approximately 300,000 inhabitants with a daily treated water flow of 100,000 cubic meter per day. A general overview of the plant is presented in this slide. As shown, the plant not only treats wastewater but also produces and utilizes biogas and contributes to the energy recovery. The mentioned wastewater treatment plants have a complex structure and utilize various stages and technologies to treat wastewater and to remove the pollutants. Pre-treatment stage. This stage is used to remove larger impurities such as solid waste, sand, and other sedimentable material. This helps prevent clogging and damage to equipment in sequence treatment stages. Primary sedimentation. In this step, heavier particles settle at the bottom of the basin, leading to the separation and removal of larger solid impurities. Activated sludge technologies. Activated sludge is a biological process in which bacteria are used to break down organic substance in the wastewater. Nitrification, denitrification. This is a crucial process that involves converting ammonia compounds into nitrate, followed by denitrification, which reduces nitrate to gaseous nitrogen. This process helps reduce nitrogen concentration in the wastewater. Secondary sedimentation. The treated water is then directly to a secondary sedimentation basin where fine particles and flocks resulting from the treatment process are separated. Anaerobic digestion of sludge. The resulting sludge is transformed through anaerobic digestion into biogas. The study found that the main source of greenhouse gas emission is the use of electricity, with the wastewater treatment stage being the primary contributor to greenhouse gas emission, followed by the wastewater collection and wastewater discharge stages. The wastewater treatment stage also have the highest energy consumption, accounting for 82% of the total energy use. As shown in the figure on the right, the primary contribution to the greenhouse gas emission is from the treatment process, with 51% being methane emission, mainly due to the biogas production within the wastewater treatment plants. The second major contributor to greenhouse gas emission is the electricity consumption, 40%, calculated as the electricity consumed from the grid during all stages of the process. The smallest contribution is from nitrous oxide, 1.6%, which is mainly from untreated water. There is a growing contribution from methane from untreated water, 3.5%, and nitrous oxide in the effluent, 4.8%. Regarding the plant's operational cost, only 11.7% is attributed to the energy consumption. This is because a significant portion of the energy is recovered from the biogas production. The remaining 88.3% is due to the use of chemical agents, employer salaries, facility maintenance, and so on. The highest energy consumption is allocated to the wastewater treatment, 90%, while the remaining 10% is used for the wastewater collection. The energy performance indicator for the wastewater treatment plants are presented in this table for different stages, for example, for collection, treatment, and discharge. Some of the important indicators can be mentioned here are the energy consumption for transporting wastewater to the treatment plants 0.02 kWh per cubic meter, the electricity consumption for wastewater treatment 0.18 kWh per cubic meter, the electricity consumption for 1 kg of organic matter expressed by biological oxygen demand removed. We have this indicator 0.98 kWh per kilogram organic matter removed. Energy production for the eliminated mass 0.04 kWh per cubic meter. The total electricity produced from the biogas represent 100%. And also we have the biogas produced per kilogram of organic matter removed, 0.11 normal cubic meter per kilogram of organic matter. In recent years, the concept of sustainability for wastewater treatment plants has evolved significantly. As a result, numerous improvements have been implemented to enhance wastewater treatment due to the undeniable importance of water as a valuable resource. One of the key aspects is the focus on reducing energy consumption. This slide presents various solutions to optimize the energy efficiency of the treatment plants at each phase: collection, treatment, and discharge. Among the options presented are using an efficient pumping system to minimize energy consumption, improving the energy efficiency of aeration equipment to reduce energy consumption in wastewater treatment processes, optimizing the anaerobic digestion process to efficiently use organic matter and produce biogas, which can be used as an energy source, and integrating renewable energy sources into the treatment plants such as solar panel or wind turbine to reduce reliance of traditional energy sources. These strategies contribute to increasing the sustainability of wastewater treatment plants with a positive impact on both the environment and operational costs. The concept of smart cities communities represent an integration of various domains: social, economic, and environment towards sustainable development. These smart cities share a common goal: improving the well-being of citizens and society through integrated urban planning and management. Wastewater treatment plants are gradually becoming a key element for such cities. The concept of a smart sewer system involves wastewater treatment plants not only efficiently treating wastewater but also enabling the reuse of effluent, also the energy generation and fertilizer production. A notable example is given by Sweden, where a city has developed a project where the wastewater treatment plant is associated with the local power plant, contributing energy from renewable sources. Key criteria of this concept include conserving natural resources for future generations, minimizing the water footprint, producing energy from wastewater sludge, ensuring the self-sufficiency of the wastewater treatment plants, both in terms of heat and electricity, and supplying surplus energy to power external urban installation. Thank you for your attention.